Hello everybody, thank you for coming here today to listen to this presentation on power-constrained trajectory optimization for wireless UAV relays with random requests. My name is Matthew Bliss, presenting here today on behalf of both myself and Professor Niccolo Micheluzzi from the Purdue University School of Electrical and Computer Engineering for the ICC 2020 conference. UAVs and wireless networks have great potential to bring extra capacity to hotspot areas, provide network coverage to rural areas, and behave as mobile relays for IoT devices. UAVs promise to bring increases to network performance due to their high degree of mobility, maneuverability, and enhanced line-of-sight link probability. UAV deployment strategies in the research have already gone a long way to increase the spectral efficiency, maximize the total service time, and minimize UAV energy consumption while subject to quality of service constraints on the network. In previous research, in fact in a 2016 paper, the limited battery capacity of the UAV is considered, but packet transmission is pre-scheduled. In a 2017 paper, the trade-off between energy efficiency and rate maximization is explored, but it serves only a single user continuously. In the 2019 paper, UAV energy consumption is minimized, but communication scheduling is not done adaptively. Users are served whenever it's convenient for the UAV's objective. An open problem, then, in the research is that of random data traffic. In this case, users may be spread over a wide geographical area, and requests from the ground nodes may arrive randomly in both time and space. The UAVs optimize their objective by adjusting their trajectory, and they need to balance between short and long-term goals. Our previous work, the 2019 Globecom conference paper, considered a simple case with 2 ground nodes and 1 serving UAV. In this paper, we considered the unconstrained delay minimization problem, meaning no UAV power constraints. In this paper, however, we do consider the case of densely deployed ground nodes and a UAV power constraint. You may be wondering, why do we care specifically about an average power constraint on the UAV? The answer to this is that hovering in general is not the most energy efficient speed for rotary wing UAVs. By considering the average power, there's actually potential to exploit the UAV mobility in order to accomplish 2 things. The first is that we can actually improve the network performance, which makes sense, but 2, simultaneously reduce the UAV power consumption. So, to start, we'll introduce the system model, state the optimization goal, then formulate a semi-Markov decision process to analyze the optimization goal, present a unique 2-scale inner and outer policy decomposition, then analyze the results, and discuss a couple of future research directions. So our ground nodes in the circular cell of radius A are distributed uniformly with an intensity lambda g. These ground nodes generate random data traffic of size L bits each to be transmitted to the base station, which is at a fixed height in the center of the cell, height hb. Each ground node generates uplink transmission requests according to a Poisson process with rate lambda p. Due to severe path loss between the ground nodes and the base station, a UAV is deployed to relay the data traffic between the two. This UAV flies at a fixed height HU and is subject to a maximum speed constraint Vmax. In addition, we model the UAV power consumption, which in general is a function of both the communication and the mobility processes. However, because mobility far exceeds the communication power, in this paper we just model the mobility. The power consumption model follows from the source at the bottom of the page and is also validated experimentally. In addition, the power model is non-convex and as a function of the forward flying speed v. And again, to reiterate, hovering is not the most energy conserving speed. So our communication intervals experience line-of-sight links, and uplink transmission requests are served by the UAV using a 2-phase decode and forward protocol. This follows a fly-hover communicate strategy, which is referenced in the citation at the bottom of the page. New requests are dropped while the UAV serves current transmission requests. However, in our ongoing journal extension, they're served directly by the base station. So to explain this 2-phase decode and forward protocol using the fly-hover communicate strategy, consider first a UAV in an initial position QU and a ground node in position QG. First, the UAV selects a new position QGU and flies there at a constant speed V1. Once it's in this new position, it receives the data payload from the ground node. Then the UAV selects a new position QUB and flies there at speed V3. Once it's in this new position, it transmits this received data payload from the ground node all the way to the base station, thus completing the communication interval. The trajectory just shown was one single realization of this problem, one possible initial UAV radius, ground node request radius, and angle between the two. This single realization is what is covered, or a variation thereof, in previous literature. In this paper, however, we want to determine a UAV trajectory strategy when any number of these realizations may occur one after another. In this case, what is optimal for that single realization may not be optimal for all realizations in an average sense of whichever optimization goal we're trying to maximize or minimize. Overall, our optimization goal is that of a constrained average delay minimization problem, subject to an average UAV mobility power constraint. Again, what is optimal for a single request may not be optimal in an average delay sense, and so this problem is not trivial to solve. With that, consider delta U of C the delay cost of the youth communication phase, E sub U the energy cost of the youth communication and preceding waiting phase, T sub U the duration of the youth communication and preceding waiting phase, M sub T the total number of requests served up to time T, and mu the trajectory policy of the UAV. The overall goal, to minimize the expected average communication delay, given by the following expression, which is a sample average of the delay cost divided by the amount of time, or the number of requests served up to time T. This is subject to the average UAV power constraint, which is the ratio of the total sum of the energy cost divided by the total duration. This must be less than or equal to the value P average. This problem is inherently difficult to solve due to the denominator term T sub U in the average power constraint. This is a policy-dependent term, and so it poses a difficult problem in standard dynamic programming techniques. However, this constraint can be expressed equivalently using Little's theorem as E bar mu minus P average T bar mu less than or equal to 0, where those following E bar mu and T bar mu terms are the energy and time metrics defined by the sample average of the amount of energy expended and duration up to time T. To deal with the inequality constraint, we pose it as a Lagrangian dual problem, and then we maximize over this dual variable nu. To do so, we formulate this optimization goal as a semi-Markov decision process, first describing the states. In the waiting states, they're characterized only by the UAV radius, as no ground node position is needed when there are no active communication requests. The communication states are characterized by the UAV radius, the ground node request radius, and the angle between the two. For some state S and an action A, the cost is given by the following expression in red, delta SA plus nu ESA minus P average TSA, where delta SA is the communication delay accrued to serve a single ground node request. TSA is the duration of this action of the chosen UAV trajectory, and ESA is the energy expended throughout this duration. Waiting state actions specifically are characterized by the radial velocity and angular velocity component VR and theta C. The action lasts for a delta sub 0 second, and then the UAV position is updated accordingly. The cost of action A from state S, in this case, actually does not have the delta SA term, as the communication delay is 0 for waiting states. After the UAV moves, it re-enters a waiting state with a probability that comes from the Poisson distribution and the sampling time delta 0, or a communication state otherwise. If it's in a communication state, then the ground node distribution is uniform within the circular cell. Communication state actions, on the other hand, are characterized by the endpoint and the specific trajectory that we described earlier that moves the UAV there, meaning the intermediate points and the speeds. The action duration in this case is delta SA, which is also the delay to service the single request. The cost of this action actually does incorporate both the delay and the energy expenditure, as well as the time duration, which is the same as the delay in this case. This system model does not account for the queuing of requests, however. As a result, the UAV returns to a waiting state in the new position with a probability of 1. We now wish to reformulate the original optimization goal in the context of the SMDP, letting pi mu s be the steady state probability of a state S in the SMDP, and L nu S mu s be the cost of taking an action from the policy from a state S. Using Little's law in the context of the SMDP, we can rewrite our original optimization goal as the following expression. Notice, however, the denominator term, which is the probability of being in a communication state, is in general policy dependent, and this presents a challenge as standard dynamic programming techniques do not account for denominator terms that are policy dependent. As a result, however, the troublesome denominator can be shown to actually be policy independent and only dependent upon the Poisson arrival process and the sampling rate delta 0 in the waiting states. It can be taken out as a positive constant. In fact, it's now solvable with discretization and standard dynamic programming techniques as a result. For waiting state actions, the steady state probability pi mu only depends on the radial velocity and not the angular velocity component. This is because the ground nodes are uniformly distributed and only the angle between the UAV and the ground node matters. For communication state actions, the steady state probability only depends on the end radius RUB and not the intermediate points and speeds. For waiting state actions, this decomposition entails that the radial velocity component is solved by the SMDP in the outer decision process, and that the angular velocity component is done in the inner decision process through a simple optimization or search. So given the radial velocity component and the UAV radius, the inner optimization seeks to solve for the angular velocity component that minimizes the power consumption. The inner optimization greedily minimizes this cost function with respect to the angular velocity, and the outer decision selects the radial velocity with the long-term average in mind. For communication states, the target end radius RUB is selected in the SMDP in the outer decision process. The intermediate points as well as the speeds are solved in the inner decision process through optimization or search. So given the state and the end radius RUB, we solve the following problem, which accounts for the delay, duration, and energy expended throughout the trajectory. The inner optimization greedily minimizes the cost function with respect to those variables except for the target end radius RUB. And the outer decision selects the end radius of the trajectory with the long-term average in mind. To solve this SMDP, we discretize the state space and then solve the problem through value iteration. First, we look at the optimal waiting phase policy for the case of a small data payload. In this situation, the UAV moves to an optimized flying radius in order to conserve power. This is because the data payload is small and the communication phases are smaller, and so the UAV spends more of its time in the waiting phase, whose goal is to minimize the power consumption because it's not serving any requests. In the large data payload case, this shifts a little bit, and the UAV seeks to place itself in the center of the cell in anticipation of the large communication phases that it will receive in the future. For the optimal communication phase policy, we have an example here for a fixed UAV radius and ground node request radius, but varying angles between the two. As you can see, the initial UAV position and ground node position and the corresponding UAV trajectory. What's interesting is that in phase 1, we fly to the ground node to receive the data payload, and in phase 2, fly from this next point to the end radius RUB to transmit the data payload to the base station. The optimized end radius for all of these different angles is actually the same at 178 meters, and the speed of both phases for all of these different states is 29.1 meters per second, although the maximum speed is 55 meters per second on the UAV. Finally, we look at the case of the large data payload, and we compare our optimal policy to that of two heuristic schemes. The start from center is where the UAV starts and ends at the center to serve a ground node. It optimizes over one speed and over one intermediate position, and spends its waiting phases hovering in the center in anticipation of requests. The hover at center is where the UAV remains at the center and does not exploit any mobility. As you can see, the hovering consumes about 1.37 kilowatts of power on the UAV, and the average communication delay is 90 seconds. Following the optimal policy, this delay is reduced by over half while also consuming less power. In the start from center case, it fails to exploit the UAV mobility during waiting phases, and as a result, the optimal policy can provide delay performance that requires a 25% lower average power allowance than the start from center heuristic. In this paper, we addressed a major gap in knowledge, which was random data traffic with power constraints. We minimized the expected average communication delay by using a unique inner and outer policy decomposition. We showed a waiting phase policy structure that demonstrates the trade-off between delay reduction and power consumption, and we quantified the benefit by exploiting the UAV mobility compared to other heuristics in order to reduce both the delay and consume less power. In the future, we'd like to explore the effect of non-line of sight channels, consider general request arrival models, and explore the scenario when the UAV can queue requests. I hope you guys enjoyed this presentation. If you have any questions, please feel free to put them on the forum and I'll respond as soon as possible. Thank you.